Welcome to DP Tutorials by Tony Jarwa. In this teaching module, we will emphasize and elaborate on one teaching lesson, which is meter bridge, or in other words, this meter bridge is also known as the slide wire bridge. And this meter bridge is nothing but the practical form of Wheatstone bridge principle. Now, this meter bridge, it is practically used in the lab for determination of the resistance of an unknown wire. Okay, so basically it is used in the laboratory to find out the resistance of an unknown resistor. To find out the resistance of an unknown resistor. Okay, so it is nothing but the practical form of Wheatstone bridge principle. And when we talk about a meter bridge, that means we have an unknown resistance wire of 1 meter long. Now, this is the schematic diagram of a Wheatstone bridge principle, whereby we have this wooden board, and on that wooden board, we have a wire made of constantan or manganese, which is having a uniform area of cross section. So over here, I have written that there are some kind of construction which we use, we can observe in a meter bridge. So over here, this is the picture of a meter bridge, and we have this over here. There is a scale. Okay, there is a scale which we can measure, and on the scale between these 2 points, okay, between these two terminals, we have a wire which is fitted. Okay, we have this wire which is fitted, which is of 1 meter long. Okay, which is of 1 meter long. And since we know that 1 meter it is equal to 100 centimeters, so it is nothing but a wire of length 1 meter long. And we have these gaps where we can fit all of these electrical appliances such as galvanometer, okay, and also we can fit these resistance box and unknown resistance wire. So this is nothing but the meter bridge, which is nothing but a practical form of Wheatstone bridge principle. Okay, let us recall what we have learned from this Wheatstone bridge principle. Wheatstone bridge principle is given by an expression which is of the form, okay, if we have 4 resistors which are connected across the arms of the bridge, that means the ratio of these resistance are equal, or the product of the resistances of the opposite arms are equal. So we have this result which we have already known. Okay, so this is your meter bridge. Okay, now the above is nothing but a schematic diagram of a meter bridge. Now let us move on into the construction of a meter bridge. A meter bridge consists of this wire of 1 meter long. When I say 1 meter long, that means in centimeters it will be 100 centimeters, and it is made of a material which is an alloy, okay, an alloy of manganese or constantan. These are nothing but alloy. Alloy are nothing but materials which have a percentage of combination of a metal and a non-metal. Now it is made, that means this wire AB is made of material which is alloy of the type of manganese or constantan, and it should have a uniform area of cross section. And over here we have this graduated scale. This is the scale. That means over here this is your scale, and on this scale, that means we can find out the readings. And over here we also have that pencil jockey where we can find out the resistance. And number 3, an unknown resistance R is connected. An unknown resistance, unknown resistance R, that means in the form of a resistance box. So over here we have this resistance box which is connected across these gaps. Okay, when you look at this meter bridge, we have these gaps. Okay, along these gaps, this will be taken as the first gap, and over here this will be taken as the second gap. That means these are the gaps. Okay, we have this can be considered as the first gap, and this can be considered as the second gap. Across these gaps, we can connect a resistance box. Okay, across these gaps we can connect a resistance box, and across these gaps we can connect an unknown resistance. So in this form, and from this junction, okay, from this junction we can connect across a galvanometer. Okay, we can connect across a galvanometer. So that is the way how we will do the connections. Okay, so basically for when we have this meter bridge, we will use to determine, or we will measure the value of the unknown resistance. So in your exams you will be asked to derive some expression for measurement of unknown resistance by using a meter bridge. So along the first gap we have this resistance box, and let the resistance of that resistance box be capital R. Okay, be capital R. And along the second gap we have this unknown resistance wire. Okay, and let the resistance of that unknown resistance wire be X. And along these two ends of the meter bridge we have this wire of 1 meter long, which is fitted. Okay, and along these terminals, okay, along the junction points A and along the junction point B, we will apply a potential from the battery having a potential, say, of V volts, or having the EMF E. So over here we know that this is the positive potential of the battery and this is the negative potential of the battery. So for the positive potential of the battery is connected to the NA of the meter wire, and the negative potential of the battery is connected across the NB of the wire. Okay. Now across let us take that point as the point D, or the junction D. Okay. So from here, by from this junction D, we will connect across the galvanometer, and from the galvanometer, that means what is the uniqueness of drawing this line? The uniqueness of this is because there should be no crisscrossing of wires. And from this point, we will connect across a jockey, and this jockey is meant for sliding, okay, for sliding along the meter bridge wire. Okay, so let that be the jockey. So this will be a jockey, and let at some point let us find a zero deflection of the galvanometer. We have the galvanometer like this. That means over here this will be read as 0, over here this will be 30 degree, and over here this will be 30 degree. That means over here there will be the deflection of the needle. Sometimes the needle might deflect full scale deflection, but we are interested in finding this zero deflection. So we'll find the null point corresponding to this zero deflection by sliding the jockey, along the bridge wire. So from here we have this jockey J. Let this be the jockey J, and we will obtain a null point C at the point N. Okay, at the point N. So from here, by adjusting, we have to adjust the resistance from the resistance box. Okay, by adjusting the resistance from the resistance box, say, like for instance, we might take the resistance might range from 0.1 ohms to a typical range of what? To a typical range of 100 ohms. So by varying the resistance from the resistance box, okay, we can find, and by sliding this jockey J along the bridge wire, or along this wire EB of the meter bridge, we will have to get the null point. And this null point, it always corresponds to what? To the zero deflection on the galvanometer. And suppose let the null point be obtained at the point N, and which is at the distance 1. Suppose let this point N be at a distance L. Okay, let that point N be at a distance L from the point E. Since this meter bridge, this wire EB, the full length of the wire is how much? The full length of the wire is 100 meters. We already know that it starts from 0 centimeter, and this last tip of the bridge will be 100. So if from A up to N is L, then the remaining the length Bn will be what? The remaining length Bn will be 100 minus L. So from here, it is very, very evident that we will obtain the null point, which is at a distance L from A. Okay, and the remaining length will be what? Will be Bn, which is equal to what? Which is equal to 100 minus L, which means that is this length An will be equal to L, and the remaining length, which is our Bn, which will be equal to what? This remaining length Bn will be equal to 100 minus L. Okay? 100 minus L. Then from here, if the resistance of the wire, okay, if the resistance of the wire is P, then Okay, over here, if the resistance of the wire then from here, since this wire, okay, this wire from the meter bridge will corresponds to length, since if the resistance of the wire of length L, okay, is P, then we can write that this length L, okay, let that length L, this length L will corresponds to what? To the resistance P. So we already know from previous formula that there is a relationship between length and there is a relationship between resistance. Over here, let the resistance be what I have written, P. So let the resistance of the wire of length L be equal to what? Be equal to P. So over here we have written that this is P, and from here we already know that the resistance is directly proportional to the length. Using this formula, we already know that the resistance R of any wire is directly proportional to the length and inversely proportional to the area of cross section, which means that from here R is equal to what? R is equal to rho L by A, where this rho is the resistivity of that material, okay, which implies from here that this P will be equal to rho L divided by A. What is this rho? We can mark this as equation number 1. This rho is our resistivity. This rho is the resistivity of the material of that wire. This rho is the resistivity of the meter bridge wire, okay, of that meter bridge wire, Similarly, when you observe from the schematic diagram, okay, the remaining length Bn, which is equal to 100 minus L, even that also will have resistance. So this will correspond, that length of the meter bridge will correspond to what? That length of the meter bridge will correspond to one resistance. We have given this resistance, let P be the resistance corresponding to L, and even this length Bn, okay, will correspond to another resistance. Let us name that resistance as what? As Q. Okay. So when you have a wire, that means when you have a wire of length L, okay, when you have a wire of length L and a certain area of cross section, it is certain to have what? It is certain to have resistance. Okay? It is certain to have resistance. So that is why we have named this wire of length L, let the resistance be P, and the wire of length 100 minus L be Q. So that we can find out the resistance of this unknown by using what? By using this Wheatstone bridge balance condition. Okay, by using that Wheatstone bridge balance condition. So from here, we will just do the write up. Let Q, okay, let this Q be the resistance of the wire of length 100 minus L. Then what do we have? So using that same analogy, Q will be proportional to 100 minus L, which implies that this Q will be equal to what? Will be equal to rho L 100 minus L. I mean, since the length is 100 minus L, you have to write 100 minus L, length 100 minus L divided by what? Divided by the area of cross section. Since the area is uniform, so that is why we have to write A. Okay, area is uniform. We have written somewhere on this area, it is having what? A uniform area of cross section, so that is why we have written as A and A. Let us mark this as equation number 2. So when you slide this jockey along this bridge wire, this is the jockey, there is the pencil jockey on this particular point. This is your one, that is your pencil jockey. When you slide this pencil jockey along this meter bridge wire, then you will find what? Then you will observe a zero deflection on the galvanometer, which is known as your null point. So when the bridge is balanced, it means that we obtain what? We obtain the null point on the galvanometer. So at this condition, it follows from Wheatstone bridge principle that the ratio of the opposite arms should be equal. So which means that from here P, okay, P by Q should be equal to what? R by X. So from here, this resistance P will correspond to L, this resistance Q will correspond to this 100 minus L, R will be from the known resistance from the resistance box, and X will be that unknown resistance. Okay? X will be that unknown resistance. So from here, we will just write that balance condition. This, we will use this expression to write what? To write this balance condition. Okay? And balance condition, it should be used by this. So from here, it follows from Wheatstone bridge principle that P by Q will be equal to 1, will be equal to R divided by X, where X is our unknown resistance. So from here, it is very evident that the resistance, from equation 1, okay, from equation 1, that means this will be equal to what? Rho divided by L, rho L by A, okay, rho L by A, and this will be equal to 1. This will be equal to rho 100 minus L divided by A, and this will be equal to 1. This will be equal to R divided by X. Some of the terms from there gets neutralized, like this rho and rho will get cancelled, even A and A will get cancelled. So the final expression, will be of the form of L divided by 1, 100 minus L, and this will be equal to R, okay, R divided by X. So our target is to find out this X. Okay? We can find out that X by cross multiplying X this side. So from here, this will be 1. This will be 100 minus L. We will cross multiply this side and this side. We will have 100 minus L divided by L into 1, into capital R. Okay? Into capital R. So this is the expression. Okay? This is the expression for finding the resistance of an unknown wire by knowing the length. So if you, this is that expression, this is that expression. So by knowing, so if you know the values of L, okay, if you know the length of the balance point, okay, if you know the value, if this is known, okay, this is, what is this? This will correspond to the balance length. Okay, this is known as your balance length. Balance length corresponds to null point or zero deflection on the galvanometer. And if we know the taken values of R, okay, this will be 1. This will be the values taken from 1, taken from the resistance box. Okay, this will be the value taken from 1, taken from the resistance box. So once you know the values of R and once you know the values of L, then you can find out X. So in your laboratory, after you find X, that means that resistance of the unknown wire should be expressed in ohms. Okay, should be expressed in ohms. So just go through that brief derivation so that you will get a clear emphasis of this analysis. Thank you.